Welcome to our quantum deep dive. Today, we're exploring one of the most profound puzzles in all of science, drawing from the fantastic essay on Antibaryons by Jörg O.A. Schnippet.
We're going to tackle a question that sounds simple, but, well, it underpins our very existence.
You know, according to our best understanding of the Big Bang, the universe should be totally empty, just nothing but leftover energy.
That's right, because matter and its mirror image, antimatter, should have been created in exactly equal amounts. And then, poof, they should have completely annihilated each other.
And yet here we are. It's the universe's greatest cold case. And today we're going to investigate the key clue, the antibaryon.
Okay, let's dive into this. Here's our roadmap for this explainer. We'll start with the cosmic crime scene, introduce our main suspect, follow the investigation, and then look at what it all means for the future.
All right, let's set the scene. In the very first moments after the Big Bang, pure energy was converting into particle-antiparticle pairs. So for every single particle of matter, a particle of antimatter popped right into existence alongside it. And when these opposites meet, they annihilate each other. They just turn right back into pure energy, like gamma-ray photons. So you can see, a perfectly balanced creation should have led to a perfectly empty universe. So here's the crucial point. Something wasn't perfectly balanced. For every 10 billion particle-antiparticle pairs, it's believed there was just one single extra particle of matter that somehow survived.
And that tiny, tiny imbalance, that's the reason everything exists. We're talking stars, planets, and us. This whole mystery, it has a name, the baryon asymmetry problem.
To understand what's missing, we really need to understand its twin. So let's move on and properly meet our particle of interest, the antibaryon. To put it simply, if baryons are the basic building blocks of all the matter we see and touch every day, then antibaryons are their exact antimatter counterparts, their perfect, spooky twin. Now, what's really fascinating is how they're both identical and perfect opposites at the same time. I mean, look at this. An antiproton has the exact same mass and spin as a proton, but its charge and this other quantum property called the baryon number are completely flipped.
Yeah, that baryon number is basically a quantum accounting trick. Regular baryons, like our trusty protons, get a score of +1. So by the rules of physics, their antimatter twin, the antiproton, has to get a -1. It's all about keeping the universe's books balanced.
So these are the key identifying features our cosmic detectives are always looking for. They're fundamentally the same in some really important ways, but critically, they're perfectly opposite in others.
You know, antibaryons weren't just stumbled upon by accident. Oh no. They were hunted, following a trail of theoretical breadcrumbs that led scientists to build some of the biggest machines in human history. And the hunt really began way back in 1928 with the physicist Paul Dirac. His equation, which you see here, well, it described electrons, but it had two solutions. One was for the electron we all know and love, but the other seemed to describe an anti-electron with a positive charge. That was the first clue. And this just brilliantly illustrates that whole journey from pure math on a chalkboard to an actual physical discovery. I mean, it took nearly 3 decades from Dirac's prediction to finally find and confirm the antiproton. Incredible patience. So today, places like CERN are basically antibaryon factories. It's this 4-step process. You collide, you create, you separate, and then you store. That's how we get our hands on these incredibly elusive particles for investigation. Okay, so we can find antibaryons and we can even make them. But how does that actually help us solve our original cosmic crime, the case of the missing antimatter?
Well, the answer might lie in a really subtle flaw in the universe's apparent symmetry. It's a phenomenon called CP violation.
In a perfectly symmetric world, right, a particle and its antiparticle would behave as perfect mirror images under any and all circumstances. CP violation means that mirror, it's just a little bit warped. This tiny, subtle difference could be the motive we've been looking for. If antimatter decays or just interacts a little bit differently than matter, that could be the reason one survived that initial chaos and the other vanished. So you have experiments like LHCb, and what they're doing is painstakingly comparing the decay of baryons and antibaryons, looking for any tiny discrepancy. And here's the twist in our case. They have found some CP violation. But, and this is a big but,
the amount they've observed so far just isn't nearly enough to explain that 1 in 10 billion surplus of matter. The motive is there, but it's not strong enough to convict. Now, this entire investigation has led to some really surprising spin-offs. While we study antibaryons to understand the distant past, they might also completely reshape our future. So on one hand, you've got the sci-fi dream of antimatter drives for spaceships, and that's theoretically possible, but it faces these enormous technological hurdles, like just making enough of it and then figuring out how to store it.
And then on the other hand, a form of antimatter is already being used in hospitals every single day. PET scans are a direct medical application of that annihilation principle, but they use the much smaller anti-electrons.
And get this, researchers are now exploring using antiprotons for cancer therapy. The idea is they could deliver this highly concentrated burst of energy directly to a tumor, which would minimize damage to all the surrounding healthy tissue. It could be even more precise than current therapies. This one is highly speculative for sure, but some theories suggest that the unique properties of trapped antibaryons could one day be used to create ultra-stable qubits, the building blocks of quantum computers. Wild stuff. So where does our investigation stand right now? We have a prime suspect, that's CP violation, and we're busy gathering evidence. But let's be clear, the case is far, far from closed. And these are the hard, practical realities. As a fuel source or as some common technology, antimatter is going to remain firmly in the realm of science fiction, at least for now, because of these immense challenges. Beyond all the technology, this research really forces us to ask these incredibly profound questions. Like, is our universe just fundamentally asymmetrical? Is what we see just one little domain of matter in a much larger cosmos that might contain vast hidden regions of antimatter? So the crucial point is that every single experiment with antibaryons isn't just about the particles themselves. It's about testing the very foundations of physics as we know it.
The case of the missing antimatter absolutely remains open, but the clues we're uncovering along the way are literally rewriting our understanding of the universe itself.
We really hope this explainer has shed some light on the incredible world of antibaryons. A huge thanks again to the foundational work of Jörg Owe Schneepatt for making this topic so accessible.
To learn more, be sure to visit schneepatt.de. Thanks for joining us, and goodbye for now.
Schneepatt.de is a private project by Jörg Owe Schneepatt dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.